Okay, lights, camera, computer, voice changer, it's all live and working?
Yes, sir. All systems are operational.
Okay, good. Fire it up on my mark. 3, 2, 1, go.
Systems booting, sir.
Initiate telegram sequence. Are you ready for this, sir?
I think so.
Do one more test run of the voice-changing device first.
Does it sound all right? Do I sound gay?
Yes, you do sound very gay. Perfect. Now, Sergeant Lopez and I are going to be monitoring you from right over there. Do you remember the plan exactly as we discussed?
Yeah, perfectly. I know what to say. I got this.
Good. Now go ahead and log into the burner account.
Okay, I'm online.
Okay, fire up the voice changer. You're on your own from here, cowboy.
Okay, I got this. Grabbing link from the BitChute channel.
All right. Look at this. It's a Rollin Ramble. And I put out a poll asking out of 4 options what you guys would want, since I have a tendency not to get enough good answers whenever I ask more open-ended what you want. And what won by a really large margin, I mean 3 times more than even the next choice up, was talking about how technology, specifically computers, but tech in general, has stagnated since 2003, and we've settled into what is known as incrementalism. So the big thing with this is that 2003 is when AMD released the AMD 64 architecture, which eventually just started to be called the x86 64 architecture. This was primarily to differentiate it from Intel's Itanium, or as it is often referred to nowadays, Intel's Itanic, because it was a massive failure. Itanic was arguably, God, I even called it Itanic, one of the most revolutionary chips, or at least one of the most bold chips in terms of innovation. The reason it was a failure is that it made assumptions that basically compilers could schedule a very long instruction word, or what basically is, instead of an opcode, the actual assembly language pulls the control lines almost directly in the execution core of the chip. So explicit parallelism. There was this assumption that compilers would somehow be able to schedule that really well. The problem is that most programs don't work in a way that you can know at compile time exactly what their behavior will be like at runtime. A classic example would be my own program, JDupes, the duplicate scanner, which, if you scan a directory of 100 files, it behaves a certain way, but if you scan a directory of 100,000 files, including lots of symbolic and hard links, crossing file systems, the execution paths can diverge quite a bit, and it causes the behavior to be very different from one run type to another. So, hang on, we're going to try to get into the traffic here, but if we can't, we can't. Three cylinders of fury. Yeah, that guy behind me was way too close to me, and I wasn't really willing to risk dealing with him. So anyway, sorry about that. It's always exciting whenever you're watching one of these Rollin Rambles, and that's all I can say on the subject. Anyway, so, geez, I completely lost my place. We were talking about Itanic and how the very long instruction word thing didn't work out very well because things can't be known at compile time, and programs behave very differently. So this is also actually one of the problems that I have with the programming language Rust. Rust wants a lot of things to be known at compile time to optimize them away and to satisfy the borrow checker. But I didn't come here to discuss Rust. I'm mainly bringing it up just as a tangential point that what Intel's Itanium processor was trying to do required things to be a way that they are not. And basically, between that and AMD 64, AMD 64 won out because it was arguably incremental itself. It was really just Intel's 32-bit x86 processing paradigm extended to 64 bits. They made a few decisions in the process. For example, I believe all 16-bit operands, I don't think that those are directly supported. It's been a little bit since I've thought about it, so I might be wrong about that. But there's a reason that they don't have a Windows on Windows subsystem to run Win16 programs on 64-bit Windows, but they do on 32-bit Windows. And I'm pretty sure that's why. So, AMD 64, why is that the last revolutionary, major, innovation in computer technology? Because everything else is just built on top of the exact same foundation. If you go back to the Pentium Pro and even the Pentium MMX, this is a fascinating little story. The Pentium was Intel's last major in-order architecture. Now, they've released in-order chips, mainly the original line of Intel Atom chips, but Intel's in-order architectures died with the Pentium MMX. And technically they died with the Pentium, because if you dig into the way that the Pentium MMX worked, to support those MMX registers, they really just had to pull a trick where they overlaid the multimedia extensions, the 64-bit registers for that, also known as XMM, directly over the top of the old school 8087 floating point unit registers. The problem with this being that now MMX directly affected FPU state, and you could not use FPU and MMX at the same time without running an instruction that would clear the MMX flags so that you could then use the registers for the floating point coprocessor unit built into every chip since like the 486DX or 386DX or something like that. But yeah, it was a great way for them to make MMX available without having to deal with the problem that operating systems would have to know about it, because MMX state essentially was just FPU state. I mean, yeah, it was smart, but this was the beginning of the end, because even under the hood, you were starting to see the push towards the out-of-order execution style. They're actually, there's still things like branch prediction, whatever, but out-of-order execution wasn't there yet. In fact, the Pentium is kind of what made branch prediction and things like that mainstream in the Intel world, at least. That's why it was called a superscalar chip. It not only had these big fat pipelines, but it also tried to figure out where you were going to go with them. And so it could try to kind of go the way it thought you would go, and if it got it wrong, oof, and if it got it right, well, things ran faster. But everything really came to a head with the Pentium Pro. The Pentium Pro is a weirdo chip because it introduced out-of-order execution. Now, programs did not run in the order that the machine language instructions said to do things. Rather than whatever you wrote in assembly or compiled down to assembly running in the exact same order that you or your compiler told the processor to do it, the processor had multiple execution units. It had reorder buffers. It had these mechanisms under the hood that could now take multiple instructions in a program, and as long as those instructions did not introduce what's known as a serializing factor or serialization, those instructions could be executed simultaneously. For example, let's say you added a register, or let's say you added 10 to a register, and let's say the next instruction adds 30 to another register. Both of those instructions, assuming that the CPU had fetched and decoded both of them, could be executed. They would actually run through execution units at the same time on a Pentium Pro, where that simply wasn't a thing prior. On a Pentium or a Pentium MMX or a 386 or a 486 or the original 8086 or God knows what else, if you ran 2 editions at the same time, you would not get 2 editions at the same time. Add this. I may have misspoken there, I'm sorry. But if there are 2 editions side by side and they don't have dependencies on each other in any way, the Pentium Pro could fire both editions at once. The Pentium MMX and older does the first edition, does the second edition. Excuse me. And every single chip, every last chip out there, save for like the Atom and certain specialized embedded stuff, but pretty much every chip now has this massive out-of-order execution engine that basically takes everything that it's told to do and tries to figure out ways that it can rearrange it so that it can do some of the work that is brought up a little later before it's actually run into, so that it can do multiple things at once internally without you having to do any parallel programming at all. This is the dirty little secret behind basically every chip. The Pentium Pro is a 1995 design, and it being 2026, that basically means we've had the Pentium Pro for 3 decades now. Which means that, save for the Atom and a few niche cases, the vast majority of chips out there that are Intel compatible x86 or x86-64, out-of-order execution is the norm. And it is probably the single biggest reason that things are so damn fast today. The problem is, it takes up a lot of silicon. There's tons and tons of work that has to be done under the hood to make sure that things produce the same result, even when you change the order you do the work in. That's where things get really nasty. Now, there are obviously alternatives to this, and those are the ones that largely failed, such as the Itanium, and the Atom arguably failed because it being an in-order chip did make it much more of an energy efficient chip, but it also meant that it was very, very slow, which is why it was in netbooks that had very lightweight Linux distributions on them, like the Asus E PC. That's 3 E's if you're trying to look it up. 3 E's. And I believe it was the E701 or something to that effect. It's been a long time since netbooks were a thing. So forgive me if my memory does not help here. But anyway, out-of-order execution was really the biggie. But then the Pentium 2 fused out-of-order execution is so clumsy to say. I wish I had an easier way to say it. But it fused that with the MMX instruction set from the Pentium 2. Now, the register renaming under the hood that was part of out-of-order execution because of multiple execution ports also accommodated this 64-bit register architecture under the hood. The core of any processor since the Pentium Pro does not work like a processor seems like it should. It's this bizarro separate processor that translates what you're saying to something else. And MMX provided 64-bit wide registers that had a limited number of operations that could be done to them. The operations that you could do are what we call vectorization today. MMX stood for multimedia instructions or multimedia extensions, and the whole point was to accelerate certain things that, like audio processing or 3D graphics, needed, like matrix multiplication. Matrix multiplication is basically the thing that all of these vectorization engines do, and everything else is sort of an afterthought or secondary. But the point is, it's basically for big math. You can put big numbers in it that are bigger than the numbers that the regular registers hold, and so you can do a lot more work, and you also have the possibility to do something called SIMD within a register, or just straight up SIMD. The SIMD is single instruction, multiple data. If you want to look all this stuff up, just go look it up by the words I'm saying. I can't explain every last concept around this to you in this video, or we'll be here all night, and I'll probably run into that trailer that's freaking me out up ahead. If you wonder why I'm looking a little startled here. I don't know what that is, and I don't want to find out the hard way, so let's just get past this guy and move on. But anyway, you could take smaller values, such as what they call packed values of 8 bits or 16 bits or whatever, and you could perform, say, an 8-bit multiplication to a 16-bit result on, I don't know, with a 64-bit wide register. I suppose that would give you 4 values that you could produce a 16-bit result in. But that's the kind of stuff that you were able to do with SIMD. The whole point being, you can take a lot of data and crush it in one operation instead of having to go, okay, load this 8-bit value into this register. Okay, load this other 8-bit value into this register. So, the out-of-order execution and the SIMD vector units are the 2 major innovations in the 90s. First MMX, then the Pentium 3 introduced streaming SIMD extensions, SSE. The Pentium 4 introduced SSE2, which is actually the baseline for x86-64. So all Intel-compatible 64-bit processors have at least SSE2, which means it has a big old heap of 128-bit wide registers in addition to the floating point unit registers, and the operating system has to be aware of those to use them. But it's yet another pile of registers. Just add more registers to it, and it's wider. Now, what's different between MMX and SSE? Well, of course, over time, they realized some operations were useful that they didn't have, so they added those. SSE 4.2, I think it is, in particular, added an instruction that lets you search for, basically to do substring searching directly in assembly. Rather than having to do comparisons, you could do this sort of bulk substring scan in the actual assembly itself. And this is one of the reasons that a lot of pieces of software have optimizations where you have to have that as a minimum, because the substring search speeds up substring scanning so much so that they use it as a hack to make things so much faster in, for example, web browsers like Waterfox, for example, are real bad about this. If you don't have SSE 4.2, you ain't running a copy of Waterfox. And I think even Firefox at this point is like, yeah, if you've got a chip that old, we're just not going to support it properly anymore. Get over it. So that's how big of a deal some of these SIMD instructions are. But remember, the topic is we haven't had any innovation in CPUs, or GPUs really, since at least 2003. And the only reason 2003 is on the map there is because of x86-64. If you look at all of the SSE and then afterwards advanced vector extensions, AVX, which widened the SSE registers yet again, and with AVX 512 widened it yet again and added even more. So basically, if you look at how all this vectorization stuff has worked, basically what we've done is we've taken the Pentium Pro and we just kept extending it. We extended MMX to 128-bit with SSE. We added registers for SSE. With AVX, we added more registers, made them wider, whatever. AVX 512, more and wider. And that's basically the name of the game, is that they just add more registers, wider registers, more execution ports, more load store ports. It's just, the name of the game is we make things faster by just adding more of it. As they shrink the processes, they are able to fit more stuff on the chip, which means they can stick more cores, which means they can stick more execution ports, they can stick bigger caches, or more sophisticated reordering mechanisms, or branch predictors, or whatever. And a lot of what makes chips so fast today is not innovation, it's just make it bigger, or be a little smarter about how you predict things, or recognize more sophisticated patterns when a program starts pointer chasing through memory. And if you want to be really, really pedantic about this form of CPU innovation ending, arguably it ended with the Pentium 2. Because the Pentium 2 fused the 000 of the P Pro and the MMX of the Pentium MMX into one unified chip, and everything that followed after that was basically just extending what was already done. And that's it. And that's pretty much my whole argument at this point. Now you might be wondering, well, what about other platforms? I mean, surely, ARM64 came out, and ARM has all these fancy vector extensions, and RISC-V, whole new architecture, new vector extensions. Well, if you look at them, unfortunately, it's the same story. Yes, they might have different instruction sets. Yes, they might have some potential ideas about how to do things a little differently. But at the end of the day, the fundamental architecture is no different than a Pentium Pro. You can kind of think of a modern ARM64 chip with all the vector extensions you like as basically being a Pentium Pro with a different instruction set. And, I mean, that's really it. It still does out-of-order execution the same way. The reorder buffers work basically the same way. Caches work basically the same way. And under the hood, it's pretty much the same stuff. Just because there's variances in how you tell it, okay, do like memory fencing or whatever, that doesn't mean that it's innovation. Being different is not innovation. I mean, excuse me. I'm driving a car, but if I drove an SUV and then I got in a different SUV, that's not innovation. A company coming out with a new SUV is not innovation. Everything under the hood works basically the same. Everything inside works basically the same. They have managed to innovate in the field of enshittification. They have managed to make some cars a tablet on wheels that fails if a software update farts. I wouldn't call that innovation. I'd call that a good reason for that company to go out of business, but I digress. We're not talking about cars, we're talking about computers. Looking back in time gives you some better ideas. The old, mainframes, for example, they had different bit word widths, some of them pretty exotic. Like, there were 36-bit wide word mainframes. There were 12-bit word mainframes. There were all kinds of interesting and exotic architectures in the 60s and 70s because, for example, they might use those extra bits as a sort of flag, or they might use it to store metadata or whatever. These days, we have 64-bit architectures that have no way of addressing that much memory. A lot of 64-bit chips, the internal addressing is actually only 40 bits wide, which leaves 24 bits of waste. So it's actually pretty common for operating systems to use the upper flags of 64-bit address pointers, or the upper bits, as flags of sorts to indicate certain things, or to store values related to that 64-bit pointer. Because the architecture under the hood is ignoring those top 24 bits or, 16 bits or whatever it is, depending on your processor. They can reuse that space so that certain housekeeping functions work better or easier. That's sort of the ghost of mainframe wide words past, if you want to think of it that way. In the 80s, well, arguably the 70s and then the 80s, you had a variety of chips that were designed primarily for like workstations, like big business mini computers, or like the Microvacs or whatever. But you had all these exotic chips. I don't want to get into it. You can look up the history of various computer architectures on your own. The Spark, spelled with a C at the end, is very interesting. The PowerPC is actually also very interesting. PowerPC is actually a bi-endian architecture. It can be little endian or big endian. That's endian spelled E-N-D-I-A-N. But it's a bi-endian architecture that's selectable. So some PowerPCs have little, some have big, whereas most chips, it's hard-coded and that's the end of it. Spark had some interesting ways of handling the 32 to 64-bit transition. The Digital Alpha is a very interesting chip. The HPPA RISC is also a very interesting chip. So you can look those up if you want more information on some of the more exotic, business-oriented, big iron processor stuff from back in the day. I personally briefly owned one HP PA RISC-based workstation and several DEC Spark stations. They were interesting to play with, but they didn't have any actual value to me because I probably wasn't going to be able to browse 4chan on them on a daily basis and get any enjoyment out of it. So yeah, I have fiddled with this hardware, but it's not something that I'm super interested in. Anyway, the point is, we used to have a lot more experimentation with architectures and memory and blah, blah, blah. And over time, we have not really done that because, frankly, the Intel ecosystem is entrenched, and the ARM ecosystem also is entrenched. RISC-V is the newcomer, but it doesn't really do much that the others don't do, with the exception being it just happens to be an open design instead of being closed off behind an army of patents. So, it's more open, but it's not some kind of revolutionary architecture. It really is just, we don't like that Intel and AMD and ARM are all locked up behind a bunch of lock and key, so let's make something that's not. Fair enough, but it's not revolutionary. It's just easier to access. And that does not qualify as innovation. You basically reinvented the wheel because you wanted you wanted a wheel design that wasn't locked away behind other people's intellectual property. Now, to give you an idea, and I have to be vague about this because I may actually be doing this in the future. If I can get the kind of capital I need, there will be a silicon tape out at some point, and I'll be making chips that'll blow Intel, NVIDIA, AMD, all of them out of the water. One of the things that we've run into, due to our obsession with incrementally upgrading things, instead of attempting to make a radically divergent architecture, is we have hit something that is widely known as the memory wall. Back in the 70s and 80s, processors were slow relative to dynamic RAM. It was basically almost guaranteed if you got a 6502 and you build a Commodore 64 or an Atari 400 or an NES around it, that system, the processor is going to be able to talk to that RAM because the RAM can do the switching that the processor requests way faster than the actual processor can do anything to need another state switch. So RAM vastly outpaced CPUs in the earlier days. And then it all kind of came downhill as processor speeds blasted ahead. You get into the Pentium, Pentium 2, Pentium 3, you start seeing CPUs that are hitting 800 megahertz being paired up with RAM that might be 133 megahertz. And so, obviously, now you have a nasty situation where your CPU is waiting a lot on things to come in from RAM. Because if you have an engine that can go 800 miles an hour on a racetrack, and you are pulling a trailer that basically applies brakes if you try to go faster than 133, you ain't winning that race if someone else can go faster. You know what I mean? It's a terrible analogy, but the point is your processor can do a lot more than your RAM, and even though the processor might do bulk transfers from RAM, you can open up and batch grab like a whole row. It could still take a lot of processor cycles just to wait for a big old block of stuff to come in from RAM and get shoveled into your caches so you can actually chew through it. So even though you have this out of order execution and you've got all this sophisticated under the hood stuff that makes it so you can do two things at once, literally there's like two processor cores inside of one old school like Pentium 2 or 3 under the hood. The problem is you have to actually have the stuff, the instructions and data in your cache memory to run the instructions and data. Otherwise, you can't fill your pipeline. That's called a pipeline stall. You have to wait for the pipeline to start getting filled back up from RAM again. Well, this is where we run into a problem, because today, if I have a Ryzen 9 9950X, the thing exceeds 5 gigahertz. I mean, it is quite literally perhaps one of the first chips that actually hits the kind of goalpost that the original Crisis was assuming we would go towards. The Crisis engine was notoriously unoptimized because they assumed scaling up frequency was where things would go. And it turned out parallelism was the way things went instead. So, anyway, that's a bit of a distraction. But the point is, if I have a 5 gigahertz CPU and I have it paired up against RAM that, okay, maybe the RAM can do 6,000 megahertz, but if you look at the timings, we've got, timings in the double digits. So let's say we have, the cast latency is like 19 on a 6,000 megahertz stick of RAM. Well, that latency is, all of those timings, rastacast and all of that. It's basically the amount of frequency cycles that are wasted in between the state required, or the state changes required in dynamic RAM to unlock and open up a particular section of the memory. And if you add it up, RAM, just to open it up to access it, you might be talking about like 60, 70, 80, 90, depending on your RAM. A lot of cycles are wasted just waiting. Okay, you can run at 6,000 megahertz, but if it takes that long just to open up the floodgates, yes, the transfer's at 6,000, but every time we want to change a row or whatever, we're waiting. So the memory wall is what's really killing everything now. Because if your CPU runs out of its built-in caches and those caches don't have what you need, then you're stuck waiting on that memory wall. And if you have a large, sorry about the nose thing, seriously. I don't know what I'm allergic to, but it's killing me. Maybe it's work. Maybe I'm allergic to work. But if you have an AI model that you're training and just this massive data set that you have to do all of these floating point or integer operations across, and this is a very real thing that's killing NVIDIA right now, they don't have memory that can feed data to their GPU clusters fast enough. There are some unfortunate architectural decisions under the hood that they're never going to change, that require them to synchronize all of their GPU clusters and stuff too. That's a topic for another day. the point is, there's literally, on some of these chips, there might be tens of thousands of tiny processors inside of a GPU, and there might be 10,000 of those clustered together into one massive GPU cluster. And all of those end up sitting around waiting for the data to be shoveled in and out of RAM. And obviously there's also buses, but the RAM is really the big bottleneck. It's been the bottleneck for a very, very long time. By my recollection, RAM's been a bottleneck since really, I think actually, yeah, like the Pentium 2 might be where it all kind of started. Where RAM just didn't keep pace with CPUs, and yeah, I think the P2 is kind of the definitive era where RAM had officially just not kept up, and now CPUs spent more time waiting than ever just because RAM couldn't keep up. So to break the memory wall, we need to fundamentally rethink the way that we talk to memory, and there are a lot of ideas in this regard, but the point is, and I'm really desperately trying not to reveal my CPU architecture ideas here, but the point is that because of traps like compatibility and not wanting to cannibalize existing hardware lines if NVIDIA released something today that did not have to, for example, do the 10,000 GPU cluster synchronization due to floating point, the way that floating point math is done, it has to be in a certain order, and that means that when you have 10,000 GPUs that produce results, they all have to swap data with each other and synchronize that data, which means that after they all do their math, they all have to wait on each other to send the results to one another. And this is one of the major things that is burning out even their most recent GPU clusters. The power circuits can't handle it because they have to run dummy loads just to keep their power MOSFETs from exploding. And a lot of it is just that everything has to stop and wait for all this shuffling to happen. And guess where the results that are shuffled end up going? Oh, they go into like the HBM3 or whatever that the GPU has. It's all just going back in and out of memory. RAM is by far the biggest problem in existence. So what we kind of need is an exotic new CPU architecture that, this is going to sound weird, but doesn't use dynamic RAM at all. Completely different way of thinking about it. What if we just didn't use DRAM in the first place? Or what if we treated DRAM as a different kind of storage than just an integral part of the way that the CPU works like we do today? And that's sort of the thought I want to leave you on in that regard. Just telling you that, I feel like I've already given up too much of my architectural idea. But the problem is that even if someone were to create the architecture I've been developing in my head since like the beginning of this year, if not earlier, I can't remember exactly when I started thinking about all this. But if someone were to put this onto a chip and spit it out, the very first, biggest reason no one would accept the greater performance is that all the software stacks would have to be rewritten pretty much from scratch to use the new architecture. And the greatest enemy of a better way of doing things or a better solution is an existing solution that happens to be good enough. Now, I'd argue existing solutions for very many high-performance compute workloads, they just aren't good enough. But I swear, that compatibility issue is major. The other thing is, if you want to tape out a bunch of, whatever the minimum order is on a relatively modern chip process, you're looking at, it's measured in the many tens of millions for modern processes, and you could also be facing the very real likelihood that there's an errata in the design that you didn't catch before it went onto whatever 100 or so 3 nanometer wafers, and you just ruined an entire stack of silicon, and that's $50 million down the trash can. So yeah, the little guy ain't exactly going to be beating NVIDIA anytime soon, and NVIDIA ain't exactly going to release something that runs 5 times faster than their existing solutions and doesn't have the all-reduced synchronization for GPU clusters, because then who the fuck's going to buy Blackwell and Hopper and all that for, you know, who's going to buy their existing product lines once they release this new one? Now, you know, oh, you got more speed, but once we sell it to you, we've sold it to you. Why would you buy the old one? We've still got all this old stock. And even worse, the people who bought the old stock are going to be bitter, because if you spent tons and tons of money for a GPU cluster full of Blackwells or Hoppers or whatever, you're going to be pretty pissed off that you did not, that you bought right before this revolution that they surely knew that they were putting together. And now you're ripped off because you've got, you know, you're paying the early adopter tax times 10. So your AI data center can't compete with the other guy, so you're forced to buy this new architecture. The resentment is real. So yeah, enterprise, the big boys who can afford it are never going to do it. And people like me could never afford it. So we're in this nasty limbo where everything is just sort of stuck. We're not making progress so much as just going, oh, well, we'll add this to the engine, or we'll fine tune it. We'll bore it out a little more. But fundamentally, everything today is still a Pentium Pro or a GeForce 2 or whatever. Just because we've added on wider registers or higher frequencies or reordering to do 2 things at once, it doesn't really make a difference, because at the end of the day, it's really just the same engine, but we've been tuning the same engine for 30 years. I'm going to leave it there. I hope that this has been interesting. Leave all your questions and comments in the comment section. Have a good night, or day, whatever, I don't care.
Okay, shut it down. That's a wrap. We got him. We got you, motherfucker.
Fuck yeah, how did I go?
You absolutely nailed it. Well done.
Well done, sir. Bravo.
Hell yeah! We got you, bitch!